All right, I'd like to go ahead and introduce our next two speakers. So our next two speakers, Adam Shook is the principal consultant at Data Contestant, and Dan Sun is a tech leader at Bloomberg, and they're going to talk to you about an Accumulo connector, or Accumulo connector for Presto. So, Adam.
Thank you, Dan. Ooh, I moved it. Thanks everyone for coming and take a look at our talk. Today, again, my name's Adam Shook. And I'm joined with Dan Sun here from Bloomberg. We're going to be discussing our Presto Accumulo connector that Bloomberg has recently open sourced and actually pushed back to the Presto community. They accepted the pull request after sitting about 6 months on GitHub just last week, so I'm very happy with that. So this connector will actually be shipping in the next release of Presto. Today we're going to be talking about the Presto Accumulo architecture, just kind of giving an overview of what Presto is, how it works, how the connector interacts with Accumulo, and kind of dive into some of the technical details about Presto's predicate pushdowns and how the Accumulo connector leverages those. Also the kind of built-in secondary indexing and metric optimizations that we've built to get very fast query times. Some additional features of the connector as well, and then Dan's going to be covering the Bloomberg use case, and kind of what drove this connector in the first place. So a little bit about Presto itself. It is an open source ANSI-SQL query engine. It started at Facebook in 2012 to kind of solve a use case of wanting to write interactive analytics at scale. It follows kind of the MPP database implementation methodology and architecture. And their goal here was kind of to fit the middle ground of very, very fast query times with very expensive software and hardware solutions versus kind of the slower, Hive type executions of very inexpensive software, free, and kind of expensive hardware but less expensive than kind of custom solutions. So they started working on Presto then. So the architecture itself for Presto, there are two services. These are Java services. It's implemented in Java. Coordinator there's a standalone process which is basically responsible for receiving queries from the clients. It receives a SQL query, parses the query, validates the syntax, all those things, actually plans the query on how it's going to move from the data tables and run through the filters, run through any joins that you're going to do, any aggregations, orders, things like that. Building that plan and then actually dispatching it out to multiple worker processes. So the worker is the thing that actually executes the query. Kind of the workflow here is we have a 4-node system with 1 coordinator and 4 workers. The client issues a query to the Presto coordinator. The coordinator then analyzes that query, builds a query plan. This is part where actual Presto connector code is executed to generate the query plan. It then builds a collection of what they call Presto splits. So it's kind of analogous to I'm running a MapReduce job, and there's all these map tasks of how to parallelize actually processing your application. These tasks are then issued out to the workers. The workers then scan from the data source in parallel to read data out of it, at which point the workers will shuffle data around as necessary. They're filtering data, aggregating, they'll shuffle data around to do like hash-based distributed joins, things of that nature. And then one worker will eventually aggregate all those results and return them to the client. And then you're happy because you got your results set. It's my one goofy image. Enjoy. So the the initial implementation was Hive. It uses Hive's metadata store, and then there are all these other connectors that people have been building over the years. There's a black hole connector, which just pipes a bunch of data to DevNull that they use internally for kind of performance testing. There's a connector for Cassandra, Hive, of course, JMX, Kafka, MongoDB. They have kind of a generic JDBC connector, which has MySQL support, Postgres support. There's a framework called Raptor, it can connect to Redis. There's a TPCH connector for generating data that a lot of the test cases actually use. Running the TPCH benchmark using those data sets. And now there is Accumulo. And someone else just started working on an H-based connector as well. So it's a very thriving community. People are actively contributing to this every day. I get blown up a lot with emails from their forum. It's great. So the actual workflow here, just kind of going over a similar step, but tying in the Accumulo pieces. The client will issue a query to the coordinator, and the coordinator is going to leverage these indexes that I'm going to talk about shortly, as well as additional optimizations that we've built into it to figure out what ranges from Accumulo, either actual ranges of row IDs or what kind of collection or set of row IDs we want to pull out of Accumulo. So that process there is running it. It's doing a lot of different optimizations in index querying to build a collection of Presto splits. And in the concept of, I want to just count how many rows are in this table. What the connector will do is make one Presto split per individual tablet range. Whereas if you're querying the index and actually using the index, it will pack like 10,000 row IDs per Presto split. So it's just, the split then gets serialized and sent to a worker, and inside of that are all these different Accumulo range objects that it actually uses to scan data from Accumulo in parallel using the batch scanners. So all the workers then, they fire up their batch scanners, they pull data out of Accumulo and converting it into Presto's internal model. It's more of like a streaming API than an actual convert these things to this object. But conceptually, it's converting Accumulo data into something Presto can actually understand. At which point then Accumulo's job is done. Presto takes over from here, filtering anything that it needs to filter, doing any distributed hash joins, grouping data, ordering data, all the types of things that you can do in SQL. So really what we're doing here is just using Accumulo as the actual data store. So a lot of other people have gone and implemented like a Mongo connector. So you've went and are kind of querying Mongo for documents and converting them to something Presto can actually understand. Anything good? So when we kind of looked at this problem, and Dan will go into the actual use case more, but we're trying to, by building a higher level SQL API, we can expand the use of people using Accumulo and how they interact with it at Bloomberg. So when we looked at this, we're like, okay, well, we have to map this relational data model to Accumulo's data model. We have to figure out how we're going to load data. So you can load using SQL insert statements, or you can use a Java library, which is the same code that the Presto connector actually uses. So it's kind of trading off ease of use versus throughput here. We, of course, want to use secondary indexing mechanisms that are kind of common design patterns of working with Accumulo. We need to have a concept of external tables, so when you delete or when you drop a Presto table, it doesn't actually delete your data. We also realize that people store data in different ways. So while we need to have kind of an out-of-the-box solution to create a table in Presto and start shoving data into it, we also need to have some sort of pluggable serialization framework that abstracts away a lot of the Presto bits and just kind of lets you focus on how do I turn key value pairs into Presto's model. So as we started kind of looking at this, we're like, okay, there's already this relational model that's been around for a while, where we're going to take kind of the primary key, the unique identifier of the row in Presto. We're going to map that to Accumulo's row ID. We're going to then take a column name, and we're going to map a Presto column to a column family, column qualifier pair, which can be arbitrary, or Presto will just has its own defaults. And then we're going to map the value of that cell in the row to the value of the Accumulo key value pair. So how this actually looks. At the top here, we have just a little Twitter data, 4 rows, with the ID, the name of the user who tweeted, when the tweet was created, the number of followers that that user has at the time that they tweeted. So how this maps to it, the ID being the unique identifier for that tweet, mapping to Accumulo of the row ID. We then have, we're duplicating the Presto column name, so the name is both used as the family and qualifier. These are all configurable things inside of it, so if you have specific ways you want to lay out your data, like you do at Bloomberg, you can change it, leverage locality groups and column families and all sorts of those exciting things. And then the value of the cell is the value of the actual key value pair. Here, they are human readable, because we are humans looking at this. It's actually using Accumulo's lexicoder APIs to ensure lexicographical sorting for the indexes as well as other things. So just know that it's actually bytes stored in Accumulo. So then, when you create a table, you specifically flag, I want these columns to be indexed. Some columns shouldn't be indexed because you're going to have millions of rows and there's only 3 values, and now you're going to create hotspots in Accumulo and all sorts of other design decisions. So here we're indexing the name column, the created column, and the followers column, and it's kind of a standard secondary index where we take the value of the table. Over here, say created at 12, that's a lot of digits, 12 something, and we're using that as the row ID in our index table, and the column family is a concatenation of the column family qualifier of the Presto column, and then the column qualifier is the actual row ID. So what this enables us to do is when you see a query that says, I want to know, give me all the rows where the followers count is 233,076, you query the index table. From that, you get the row IDs, and then you query the actual table. Fairly common design pattern when working with this. So then brings us to actual predicate pushdown. So Presto exposes filters in these where clauses of a query, which we'll see soon as an example. And it tells you which columns you're actually choosing. So if you have a table with hundreds of columns and you're only selecting 3 of them, it'll tell you you only want these 3 columns. So that's one thing Presto will tell you. In addition to that, they're going to give you the ranges on the actual values. So when you say where event time is between this date and that date, it will tell you what those days are inside of it. So what we can then do is use these secondary indexes that we've built to figure out which rows we're actually going to read. Rather than reading every single entry in Accumulo and having Presto filter out that data for us, we're basically pre-filtering it by saying we're only going to bother reading these handful of rows from the table. And we do that through the indexes. And then we go and configure our batch scanner appropriately inside of the worker nodes to do that. So an example here, we're selecting 3 columns from our table. The ID is the row ID. Created and followers columns as well. Between January 1st, 2011 and May 31st, 2011. And the followers count is this very specific value for some reason, probably because it's an example. So from that, the Presto APIs will tell you, you're looking for these 3 columns, the ID, created, and the followers. And here are the predicates. It's these ranges between these 2 timestamps, and the followers, it's given to you as a range, but it's still just this specific value. And if you have multiple predicates, it will give you all of them. What it doesn't do is if you have any, let me back up. The predicate has to be a conjunction between all of the columns. So if this had between these dates or followers, Presto would not tell you anything about that, and you'd be scanning everything. So it only supports very specific queries about what Presto will tell you. So a lot of these Boolean ands between things. So what the connector does then, during query planning, this is all happening in the coordinator, it goes and it scans the index. And it says, it does a range scan here in blue on the followers tables to pull back all of the entries that would meet that predicate. Here it's these 2 tweet IDs starting with 24 and 25. And it will also read the followers index as well for that value that was asked for, which would be a single key fetch from Accumulo, and pulls back those row IDs. And then the connector will do set intersection. So rather than reading 3 distinct row IDs, it will look at all of the columns and say, what predicate is this going to satisfy, and get the smallest number of row IDs to scan. In this case, it's 1. In common cases at Bloomberg, it's thousands and millions of row IDs that we're pulling out at once. So this set of range IDs are then serialized to JSON objects and shipped off by Presto framework to a reader, where it will unpack those set of ranges, and it will programmatically say, I'm going to fetch the ID, which it's going to get automatically because it's the row ID, and we're only going to pull back the created column and the followers column, and we're going to select these ranges. And then it goes off and pulls the data out of Accumulo, converts it to Presto's model, and everything else continues. So to go into kind of additional features that we've had, one is external tables, where there's a lot of metadata associated with all this, which I'll talk about shortly, in that kind of borrowing from Hive's methodology of there's internal tables, Hive owns the data. When you drop the internal table, Hive deletes the data off of HDFS. Same concept here, where when you say drop table in Presto, it will only drop the metadata. All of the data in Accumulo is still there, safe and happy. If you create an external table and the Accumulo tables don't exist, it will still create them. It will configure a bunch of iterators and other stuff on the table as well, so it still messes with the table. The only difference is it won't delete your data. Originally, our implementation was more hands-off from external tables, but it was a pain to, like, anytime we wanted to add a column, we had to go and reconfigure our iterators in this shell and all sorts of other things. So it was just easier to say, let's just kind of manage it from a configuration perspective. So the advantage here is, one, it's very easy to add a new column. From a Presto perspective, you just drop the table and add a new one. All of our tables in production are external tables. I recommend you use them because you'd be really upset if someone dropped your data, like most databases. It also enables Presto to work with existing Accumulo tables. So if you're not storing your data specifically how we're storing it here, you can go and write a new serializer, throw it on the class path, configure it on the table, and say use this serializer instead. If you are storing your data this way, then you can just say it's an external table and stuff will work. Which brings me to the serializers. There are two that come with the Presto connector. So this is the layer between Accumulo and between Presto that actually turns the rows you're scanning from Accumulo into rows that Presto can understand. One of which is called the Lexicoder row serializer, where it uses Accumulo's Lexicoder APIs to serialize, deserialize all the Java objects, integers, longs, doubles, floats, etc., into byte arrays that are then stored inside Accumulo. The other one that comes with it is called the string row serializer. It just uses string values for everything, which breaks a lot of the indexes and all sorts of other stuff. It doesn't support a lot of the things that the Lexicoder one does. Don't use it, but it's there anyway, in case you need it. Then, of course, you can go and write your own serializer for that. And then finally, well, at least about this, the Presto metadata. So when you create a new table in Accumulo, there's a JSON, when you create a new table in Presto, there's a JSON object that tracks the table name, the schema name, or the namespace name in Accumulo. That's a one-to-one mapping. Any views you create in Presto, the table properties that you create, the column definitions, and all the metadata about the columns are all serialized to a JSON object and stored in Zookeeper. Originally, it was a pluggable framework in case you wanted to store metadata somewhere else. Eventually, we kind of removed that from it because Zookeeper is already available, because you have to have Zookeeper to run Accumulo, and it was highly available and fast, and everything works well with it. There's also Java APIs that if you need to programmatically mess with the metadata, you can do that as well. It's the same libraries that the Presto library is using, connector. So all the work I've described so far was probably about 3 months of effort or so. We've been working on this for a little while. And as we kind of went into development and staging systems, we kind of were using the connector and seeing what type of queries people are running, how it's doing, and kind of dug into how can we optimize things. And what we were seeing was the queries that people were running over these systems were either very OLTP workloads of I want a small amount of data, or more analytic workloads where I want to read everything. And with an index enabled on the table, it would scan the index, which is a very expensive operation if you're scanning if you're scanning the entire Accumulo table, because you're going and pulling back potentially millions of row IDs with that. So there's eventually this trade-off where it's faster to just scan the entire table than it is to do all this overhead of scanning the index, gathering the row IDs, packaging them into Presto splits, serializing them, shipping them across your network, deserializing them, configuring batch scanners, all those steps that are involved. So with that, we needed to, the first stab was just, okay, how many rows are in the table? That's not a metric that I'm aware of that exists out of the box that's that accurate. Could be wrong. So we added a metric for how many rows are in the table. So we query the index, and it says there are 100 rows that you are going to scan, and your table has 1,000 rows in it. You're going to scan 10% of this table. Is 10% greater than or less than some arbitrary threshold, which I think the default's like 20%, but that was just a magic number I chose with that. So that was one way that we got around that. We're just going to skip the index. We're not going to use it. Obviously, at 100 and 1,000, it's different, but when you're talking millions of row IDs, it's just more beneficial to scan everything. So that was the initial part of it, and then we wanted to kind of aggregate things down further. That instead of looking at the index, we want to actually use metrics associated with that. And the whole answer, or the whole question that we're asking here, that we're trying to answer, is just how many rows in the table would be fetched based on the predicates that are given to us in the query, and is it below some threshold? If it is, great, we'll use it. If not, we won't do that. So we created another table. It's the index metrics table, which very closely mimics the storage methodologies in the index table, with the exception of instead of the row ID, we have this card, short for cardinality, qualifier, and then the value is the number of rows that have that index value. So here, the example here is the 233,076 followers. There are 2 rows in the table that have that value. So when we're going to scan Accumulo, originally we were scanning the index and pulling back the individual row IDs. Now we're just aggregating numbers. We've chopped down 2 entries in the index table to 1 entry in the metrics table. This uses the built-in combiner iterators that come with it. It's very beneficial at scale when you have a lot of different values. So rather than looking at that index, we're just looking at these numbers to make these decisions about how much of the table are we going to scan. And then with that, we started adding additional optimizations like leveraging Guava caches. We're looking at, hey, we're querying on 3 different columns. Why am I going to query them all serially? I can fire off 3 threads to pull this stuff back at the same time. So now they're all multi-threaded. They're cached inside the connector. In that, subsequent queries that are using the same predicates against the same data, the metrics can be off a little bit because we're mainly just using these metrics to make optimization decisions. So they can expire after some time, but why am I going to go back and pull the same data every second if people are querying that frequently? We then had percentage and row-based thresholds. As the tables got bigger, percentages wasn't working because it was still very expensive to use 5 million row IDs. So we added this hard threshold to say, don't use the index if it's above 1.5 million or whatever it is. We then also added short circuit reads, where if you are querying against 3 columns and one of them comes back within 20 milliseconds and says you're going to scan 5 rows out of however many million, why am I going to wait another 5 to 10 seconds for the other threads to come back and say you're going to scan 2 million rows? So what we're going to do is say, hey, 5 is below some other threshold that we have. Let's just use that. We'll let the other threads finish and cache their results locally. But we're just going to use that 5 rows, and rather than doing the row-based set intersection, we'll just let Presto filter out stuff that didn't fit. So all these things were kind of progressively implemented over time. And the last one that we did was looking at the queries that people are running. The big one at Bloomberg is event-based time queries of, I want yesterday's data, I want last week's data. And as data sets grew larger and larger, the event time metric was pretty much always that was being used. And the problem with that is every time there's an event, these timestamps have millisecond precision, so you have millions of entries where the metrics that we're tracking is 1 or 2 or 4 or whatever, whenever someone had sent a message at that millisecond. So we're still scanning millions of entries to look at these timestamps to come up with a decision that we want to use event time. So rather than just kind of hacking in something that says you should use this and ignore everything else, we kind of decided to take a more generic approach and add what we're calling timestamp rollups or timestamp truncation. where what we're doing, here's a query between some 5 days of data, and we're storing additional metrics where we're taking a timestamp at millisecond precision, and we're storing that as we always have been. And then we're truncating that down to second precision and storing that. Truncating that down to minute precision, storing that, same with hour, same with day. So now we're storing metrics that say, for this column, how many rows were in this specific day, or this specific minute, or second. So what we can do then is convert this query and say, instead of doing this long range scan over 5 days, potentially thousands, millions of things to sum up, we're instead going to kind of build a tiered system of let's scan between those handful of milliseconds. So we'll range scan that from the original one. And then we're going to move up and say, give me one single key fetch for everything at that second. Give me one single key fetch for everything at these minutes, eventually hours, and eventually days. And the example here is this. It's a small range scan, and then exact lookup on hour from 1 to 23. And then we're doing a few days and another one. So we're augmenting the range scans to kind of leverage these extra metrics for the timestamp, where instead of now doing large things, we're actually doing a handful of 2 small range scans and however many exact lookups are required. And from that, just query planning time for this, we reduced from about 5 seconds to 15 seconds down to about 15 milliseconds for query timing. And these are real people that are looking at this, waiting for queries to return. So this was huge benefits out of this kind of optimization that we had added. All right. I will now hand it over to Dan to discuss the Bloomberg's use case.
Thanks, Adam. I'm from Bloomberg Big Data team. Currently, we are building a next generation surveillance application to monitor real-time email, instant message communications to detect fraud or improper employee behavior. So we started the this pipeline, next generation pipeline last year, and then start to store all these events or violation we found through this pipeline and store into Accumulo. And then after that, we basically have a few applications on board to start to query Accumulo. And I want to share a bit our story why we end up using Presto. So our initial approach is to for every application. They have an application developer in that team, and they start to write all these server-side server-side iterators, and based on various different filter criteria or aggregations, and so basically every time they sometimes the business requirement changed, and they have to rewrite their code, and then sometimes potentially they have to refactor their code to handle oh, can I make this more generic? Maybe in future, this requirement, I can handle that and don't have to change code. But soon, we realized that is not a sustainable approach because because all these queries get more complicated, and there's aggregation involved, and there's sorting involved, and then really and often the time the application developer are not aware of all the Accumulo internals. And often the time, the code they write is not performant, and so basically it's far from our predefined SLA, because in order to make this Accumulo performant, you have to take all this parallelism in consideration, and you have to do if this aggregation, you have to do these local aggregations, and then do a global one by leveraging all this MPP database style query. So these things are basically all beyond a normal application developer stretch. Then everyone is complaining why, because used to be to handle this business requirement, it used to take a few days. Now it takes much longer time, and in order to make it performant, it takes even longer time. So everyone is missing a SQL word, which is can write a little SQL and then 2 seconds done, and then my job is done. Basically, I don't have to work here overtime to make all this, to fulfill all this performance requirement and business requirement. So so basically everyone is missing SQL. Then we decide to develop this Presto connector, and thanks to Anon, make all this SQL word back again. So and now it makes our application developer happy. right now, every application, we are basically migrating to a Presto Accumulo connector. And we are running all this application developer basically can now write a SQL query and then can send to JDBC connector and then get back the results in like most of query basically end up in like a 500 millisecond to like a 20 millisecond range because they are actually scanning a lot of data, like it can be like TBs of data based on their like queries. So actually, our application is right now on production with all this query optimization we did. We are now happy with our results, and so we are going to roll out to more and more clients potentially. So I guess that's it. Thanks.
Just a little wrap up before questions. So to review this, the whole idea here was building a higher level language to kind of leverage common design patterns that people are using on Accumulo to, you know, dramatically decrease development time and kind of get more people on working with Accumulo and using higher level languages. You can load data using SQL with insert statements. It's easier to do, but Presto has to parse that query and go through that whole process we've described. So it's just easier to kind of use the Java APIs, which will do all of the indexing and metrics for you. It's called a Presto batch writer. It mimics the same APIs. We support these predicate pushdowns through our advanced indexes and metrics. We have very fast query times for kind of the OLTP use case of give me, you know, searching for needles in the haystack. And it is open source. The piece that's in Presto it's not all the like the metrics optimizations that we have. The stuff we do have is open source. It's on Bloomberg's GitHub, github.com/Bloomberg/Presto. We will be pushing that back once we open up another pull request for them to look at. Thank you. Questions for either of us?
So you said this works with an existing table. Do you have a mechanism to build those like secondary indexes or metadata for existing data?
Yeah, so we've written a few tools that are also open source on GitHub on Bloomberg's. It's Presto Accumulo tools that like rewrite the metrics and rebuild the indexes. Because we've had a few things where we'll add a new column to a table that you want to index, and all those indexes don't exist. So there is some lag time between, you know, when you change it and when it actually will show up when you run the tool. There's certainly some work that can go into kind of working on those tools because they're just single-threaded applications. So it's there. It needs work, obviously, for it.
So do you co-locate the worker nodes with T-servers?
So they are, just by the way that they're deployed out on Mesos. Through our testing that we did in benchmarking, there's no benefits from being local to it, which kind of goes in line with a lot of the Presto community's recommendations in Facebook. They actually run Presto on own dedicated services from it. The locality optimizations are there into it, so if you do a full table scan, it'll assign them locally, but there really isn't much benefit from it. It was like milliseconds for small amounts of data, and large data, there was no difference at all. Good question.
So I noticed that your index structure puts the value as like the highest precedence. So you're looking at the value first, right, which is kind of an interesting choice. When you look at SQL, basically all of the query predicates that you have are fielded. So are you guys using that particular index for other purposes, like more of like a Lucene query syntax as well? Or have you looked at other index structures that might kind of more optimize the use of SQL predicates?
Good question. No is the short answer. It's just for these purposes we've described here. We haven't really looked at other indexing schemes for it. There have been some problems where it'll generate hotspots on it, and you get lots of "we can't split this tablet" errors. There's certainly some work that can be done into how we index things.
Any other questions?
Surprised nobody asked about visibility labels.
Tell us about visibility labels, Adam.
So we do, Bloomberg uses visibility labels on everything. The visibility labels will get propagated to the metrics and the indexes as well. They are used for scan. We have, when you configure it, there's just expected there's one super user that can pretty much do whatever it needs to do with the data. Then you can set table properties for use this specific scan authorizations, and then there are session properties that say, I am this user, so you can kind of do impersonation-based scans in the data. You don't see any of those visibility labels as far as what you're querying. When you insert data with SQL, there's no way to insert visibility labels, so you have to use the Java APIs. So it maintains all that. It's just not, I guess, as nice as it is.
So you'd made a statement, something about supporting intersections of all kinds of terms, and that looks beautiful. But you said that it had lack of support for being able to do any unions, ORs, or more complicated query
Presto
structures?
itself?
What's that?
Presto itself?
Was that Presto itself, or was that just your
So this was
your
just the
infrastructure?
connector. Presto supports a lot of the ANSI-SQL specification. So you can do unions and things like that across data sets. You can actually query different data stores in the same SQL thing, which is kind of cool. So if you want like hot data in Redis or something and your other data in Accumulo, you can join them together and things. Yeah.
Glad I misunderstood.